Hello. In this lecture, our main topic is intrinsic geometry. Before I will discuss in this topic, I will this I will set that roadmap. How my lecture is going? In previous four lectures, from section 1, 2, 3, 4, I said that the essential of tropical geometry. What is a tropical system? And based on tropical system, I plotted the graph to so-called tropical curve, and its dualization has a deep meaning as a polytope. So tropical polynomial is related to describe a polytope. And the lecture for section 4, I will discuss a two-adic phylogenetic tree. Okay, that is a main part of a tropical geometry, even if that 4 sections does not cover all of the contents of the tropical geometry. Okay. In this 5 lecture, section 5 and section 6 is main topic is far from away a tropical geometry. Lecture 5 is this. I will introduce differential geometry, mainly intrinsic geometry, and this next I will talk about the statistical learning, so-called Kullback divergence and Wasserstein distance. But based on this lecture, I will apply these theorism to a tropical geometry. Okay. So in these 2 lecture, it's not, I say again, not related to a tropical geometry, but that is a important idea to apply a tropical geometry or into a new part of tropical geometry and deep learning theory. Okay, so anyway, this is my roadmap, and let's go to our main topic, intrinsic geometry. In this lecture, I will roughly introduce what is a manifold, what is a differential manifold, what is a Riemannian manifold, and based on this, I will talk about what is a intrinsic geometry, so-called local isometry, the main topic of the lecture. Okay, so the first topic is the background of differential manifold. That is just a enumeration of some facts of the differential geometry. So if you learning about in detail and if it is not understanding this topic, see another lecture that will deal with differential geometry. That is very, very roughly summarization of the differential geometry. Okay, so start the lecture. What is a manifold? What is an n-dimensional manifold? So let M be a topological space. Then M is n-dimensional to manifold. Just not differential manifold, just manifold. If for we pick a point P, there exists a neighborhood of P, say U, but U is homeomorphic to R n. That is easy to think about our O's. This is our O's. If we take a P, or if you have this area, then even if the Earth is shape of Earth is sphere, we does not perceive this. Okay, if we are here, then if we stand this here, we understand that is a plane of 2. That means that if you take a neighborhood of P, say U, locally that looks like a plane. That if you understand this, you can understand the definition of a manifold. But that is not interesting because mathematically we cannot do anything with only this definition. So we add some condition to this definition of a manifold. So a topological manifold a manifold M is okay. Let M be a manifold, then a topological manifold with m dimensional if M is Hausdorff and second countable M has second countable basis. Okay, that is a definition of topological manifold. For many regions, that two condition is essential, and some others add another topological condition to a definition of a topological manifold. That is taste of the other. Okay. Then, what is the differentiable manifold? If throughout this chapter, I will assume that M is manifold, okay? And in this lecture, if okay, there exists two local coordinates. If we take a M as a manifold, okay, and take P, then based on P, there exists U, two local coordinates. What is the local coordinate? Wait a moment. Yeah. Here. As I said, if we take a neighborhood of P, the area is the neighborhood is isomorphic to Rn, but we think about the basis. Basis is does not unique, so whenever we take a neighborhood, we can take a different basis. Okay, this is Rn, but if we take a basis B, and if we take a basis C, it does not same the different basis. Okay, based on the map phi and psi on this overlapping area. Here. So again, to local coordinates phi and psi with this part P, such that if two local coordinate is CK compatible, which means that there exists a function what this mean? Compatible means that these two relation is well defined here and here. That is composition of like this, because if we go to here, that is, and go there. Okay, and reversely we can think about. Okay, so there exists two maps such that these two guys exist. Then we call M a CK differentiable manifold. Okay. In doing so, we can define this basis consists of like this, and these guys consist of prime different basis. So we can define a differential if a function f exists. We can define differential. But note that because the basis is does not unique, we can think about this as this aspect. So to deal with this problem, whenever we take P, the basis does not unique, we can define, we introduce some idea to, I don't know, jump at P, or an algebraic tangent plane. That definition does not, some mathematicians think that the definition does not perfect, as I said, because whenever we choose P, the basis does not unique. Okay. Okay, that is okay. And we can define, in general, let's think about the collection, the neighborhood at P, say U, and the local coordinate psi, phi, a pair of neighborhood and its local coordinate, and collect the A is a CK class if collect all neighborhood of where P is manifold. So open set is covered, M is covered by a open neighborhood. If two pair lives in A with non-empty, then two local coordinates CK compatible. As I said, there is two map exist such that literally two local coordinate with different bases is well compatible, and if there if the third pair, which is different, that guys, or CK compatible, then that guy is also A. Sorry, that is a CK class atlas. An atlas. Okay, that is the definition of CK atlas. In particular, if we difficult to understand the definition of a manifold, we instead of manifold, we can accept definition of surfaces. An orientable two-dimensional smooth manifold C infinitive manifold is called a surface. If we see as a reference O'Neill's difference geometry, instead of definition of a manifold, the author introduced a proper patch. So define a surface. For example, a sphere, a torus, and a sphere and torus and so on are surfaces.